Right now, you are expanding. Every atom in your body, every molecule of air in your lungs, every photon of light touching your retina, exists within a universe that is stretching apart. Space itself is growing, pulling distant galaxies away from us at velocities that will eventually exceed the speed of light. We have measured this expansion. We have mapped it across billions of light years. We call it the Hubble constant, and for decades, we believed we understood how fast the universe was growing. We were catastrophically wrong. Something else is expanding, something that is not space, something that operates according to rules we have never encountered, growing at rates that violate every principle of cosmic evolution we have established. These structures are not being carried along by the universe's expansion like ships on an ocean. They are outpacing it. They are growing faster than the fabric of reality itself can stretch. In 2019, astronomers discovered a supervoid so massive that it should not exist. According to our models of structure formation, the KBC void spans 2 billion light-years across, containing 20% less matter than it should. But the void is not shrinking or remaining static. It is expanding, and it is expanding faster than the cosmic expansion rate, driven by mechanisms that challenge our understanding of dark energy, gravity, and the large-scale organization of the cosmos. This is not the only impossibility. Across the observable universe, structures are emerging and growing at velocities that standard cosmology cannot explain. Galaxy clusters are colliding and merging at speeds exceeding predictions. Supermassive black holes are gaining mass faster than accretion physics allows. Cosmic filaments are extending and thickening through processes we cannot model. And beneath all these observations lies a terrifying truth. The universe contains processes that operate independently of, and faster than, the expansion of space itself. Prepare yourselves. We begin. The universe is expanding. This is not philosophy or speculation. This is observable fact, confirmed through decades of precision measurements across multiple independent methodologies. When we observe distant galaxies, we find that their light has been stretched toward longer, redder wavelengths. This redshift directly measures how much the universe has expanded during the time it took for that light to reach us. The farther away a galaxy is, the more its light has been stretched, revealing a cosmos in continuous expansion. Edwin Hubble established this principle in 1929 when he analyzed the velocities of distant nebulae. Using the 100-inch Hooker telescope at Mount Wilson Observatory. By measuring the redshifts of 24 galaxies and comparing them to their distances, he discovered a linear relationship. Velocity equals distance multiplied by a constant. That constant, now bearing his name, describes the rate at which space expands. His original measurement suggested the universe was expanding at about 500 kilometers per second per megaparsec. Modern measurements have refined this value dramatically, but the fundamental discovery remains unchanged. Space grows. But Hubble's discovery revealed something even more profound than simple expansion. It demonstrated that the universe had a beginning. If galaxies are moving apart now, then running time backward means they were once closer together. Extrapolating this motion to its logical conclusion suggests that all matter and energy in the observable universe was once compressed into an infinitesimal point. This realization gave birth to Big Bang cosmology, the theoretical framework that has dominated our understanding of cosmic evolution for nearly a century. The mechanism of expansion is not galaxies moving through space like cars on a highway. Space itself is expanding, carrying galaxies along with it like raisins in rising bread dough. This distinction is critical. Galaxies separated by vast distances are not racing away from each other through space. The space between them is growing. At sufficiently large scales, this expansion can make distant galaxies recede from us faster than light travels, not because they are violating relativity, but because the fabric of space-time itself is stretching. The expansion rate we measure depends on which cosmic era we examine. Light from the early universe, preserved in the cosmic microwave background radiation, allows us to calculate the expansion rate when the cosmos was just 380,000 years old. By feeding these observations into cosmological models based on general relativity and the standard model of particle physics, we can predict what the current expansion rate should be. The Planck satellite measurements yield a value of approximately 67 kilometers per second per megaparsec, but when we measure the expansion rate using nearby objects, employing techniques like Type Ia supernovae and Cepheid variable stars as cosmic distance markers, we get a different number, consistently different. The Hubble Space Telescope and now the James Webb Space Telescope have measured the local expansion rate at approximately 73 kilometers per second per megaparsec. This 9% discrepancy has persisted across multiple independent measurement campaigns, growing more statistically significant with each refinement in observational precision. This is the Hubble tension. The universe appears to be expanding at two different rates depending on where and how we measure it. After eliminating systematic errors, calibration uncertainties, and observational biases, the discrepancy remains. 5 sigma statistical significance means there is less than a 1 in a million chance. This is random variation. Something is fundamentally wrong with either our measurements or our understanding of cosmic expansion. The immediate suspect is our cosmic location. We exist inside the KBC void, that 2 billion light-year bubble of underdense space where matter is 20% scarcer than the cosmic average. Gravity from the denser regions surrounding the void pulls outward on galaxies within it, adding peculiar velocities to the cosmic expansion signal. When we measure the Hubble constant using nearby supernovae, we are measuring within the void. Our local measurements may be systematically inflated by the void's outflow velocity field. This explanation is elegant and disturbing in equal measure. Elegant because it resolves the tension without requiring new physics. Disturbing because it means we occupy an unusual cosmic location, violating the cosmological principle that states our position should be unremarkable. Finding ourselves inside one of the largest voids ever observed seems statistically improbable, raising uncomfortable questions about whether we can trust any measurement made from within our cosmic bubble. But the void hypothesis, while compelling, may be incomplete. The structures growing faster than cosmic expansion are not confined to our local neighborhood. They appear throughout the observable universe, at distances far beyond the KBC void's influence. These anomalies suggest that something more fundamental is occurring, processes that operate on scales larger than individual voids, and that challenge our understanding of how cosmic structure forms and evolves. Cosmic voids themselves are growing. This is expected. In regions where matter is scarce, gravity's influence weakens, while dark energy's repulsive pressure dominates. Dark energy does not dilute as space expands. It maintains constant energy density even as the volume of space increases. In dense regions filled with galaxies and dark matter, gravity can resist this expansion on local scales. Galaxy clusters remain gravitationally bound despite the universe's overall expansion. But in voids, where matter is sparse, nothing opposes dark energy's push. The voids expand faster than the cosmic average, growing like bubbles in an accelerating expansion. The mathematics is straightforward. In a region with average cosmic density, expansion follows the Hubble flow. But in an underdense region, the reduced gravitational pull allows expansion to accelerate. Computer simulations of cosmic structure formation predict that voids should expand at rates 10% to 20% faster than the background expansion rate. This prediction matches observations of small and medium-sized voids throughout the cosmic web. The KBC void is different. Its expansion rate appears to exceed predictions by a significant margin. Measurements of galaxy velocities within the void show systematic outflows that suggest expansion rates approaching 30% to 40% faster than the cosmic average. This is not just voids growing as expected. This is a supervoid expanding at velocities that challenge our models of how dark energy operates on large scales. What drives this accelerated expansion? Dark energy remains the primary suspect. The cosmological constant, Einstein's infamous modification to his field equations, represents vacuum energy inherent to space-time itself. This energy has negative pressure, causing space to expand rather than contract under its influence. But the cosmological constant should be uniform throughout space. It should not vary from one region to another. Yet the KBC void's extreme expansion suggests that either dark energy is stronger in underdense regions, or some additional mechanism is enhancing the expansion beyond what dark energy alone can produce. Alternative theories propose modifications to general relativity on cosmic scales. In these frameworks, gravity behaves differently in low-density environments. Instead of simply weakening as matter becomes scarce, modified gravity theories suggest that gravitational physics fundamentally changes, creating enhanced expansion in voids through mechanisms that have no equivalent in Einstein's original equations. These theories make specific predictions about void expansion rates, and some match the KBC void's observed behavior more accurately than standard cosmology. But the voids are only the beginning. Galaxy clusters, the densest concentrations of matter in the universe, are merging at velocities that exceed predictions. When two massive galaxy clusters collide, the event releases energies comparable to billions of supernovae. These collisions should be relatively rare in standard cosmology, because clusters form through the gradual accumulation and merger of smaller structures over billions of years. The rate at which clusters encounter each other depends on their velocities and the cosmic expansion rate. The Bullet cluster represents one of the most dramatic examples of this phenomenon. Located approximately 3.8 billion light-years from Earth, this system consists of two galaxy clusters that passed through each other at relative velocities exceeding 4,000 kilometers per second. The collision separated the hot X-ray emitting gas from the dark matter halos surrounding each cluster, creating a natural laboratory for studying dark matter's behavior during cosmic catastrophes. But the collision velocity itself poses a problem. Standard cosmological simulations rarely produce cluster collisions this energetic. Follow-up observations identified numerous similar high-velocity cluster mergers throughout the observable universe. The El Gordo cluster, discovered through the Sunyaev-Zeldovich effect, represents another extreme example. This system consists of two subclusters colliding at approximately 200 kilometers per second, creating one of the most massive galaxy clusters known. Its total mass approaches 3 quadrillion solar masses, and its collision energy suggests formation mechanisms that operate faster than standard structure formation allows. The frequency of these high-velocity mergers challenges predictions from lambda-cold dark matter cosmology. Computer simulations based on standard structure formation produce cluster collisions, but not at the observed velocities. Either the simulations are missing some crucial physical process, or the universe contains more large-scale structure and higher velocity dispersions than models predict. Both possibilities suggest that structure formation proceeds more rapidly and violently than we assumed. Supermassive black holes present an even more extreme challenge to standard growth rates. These cosmic monsters, with masses ranging from millions to billions of solar masses, reside at the centers of most large galaxies. Their formation and growth should require billions of years through the gradual accretion of matter and mergers with other black holes. Yet the James Webb Space Telescope has discovered mature supermassive black holes existing just 400 to 600 million years after the Big Bang. At such early epochs, there simply has not been enough time for black holes to grow this massive through conventional accretion processes. Every black hole has an Eddington limit, the maximum rate at which it can consume matter without the radiation pressure from superheated infalling gas blowing away its food supply. A black hole accreting at the Eddington limit can roughly double its mass every 50 million years. Starting from stellar mass black holes formed from the first generation of stars, reaching a billion solar masses requires continuous maximum rate feeding for hundreds of millions of years. The math barely works even under ideal conditions. But JWST has found supermassive black holes that exceed these growth limits. Objects like LID 568 are accreting matter at 40 times the Eddington limit, consuming gas at rates that physics says should be impossible. The radiation pressure from such extreme accretion should create powerful outflows that blow away the surrounding gas, shutting down the feeding process. Yet these black holes are somehow stabilizing the accretion flow and continuing to gain mass at impossible rates. Several mechanisms have been proposed to explain super-Eddington accretion. Thick accretion disks with complex geometries might channel matter inward along specific paths, while allowing radiation to escape through other channels, effectively bypassing the Eddington limit. Magnetic fields could play a crucial role, funneling matter into the black hole's polar regions while radiation escapes through the equatorial plane. Alternatively, The accretion might occur in brief, violent episodes rather than steady, continuous feeding, allowing black holes to temporarily exceed the Eddington limit during feeding frenzies that last thousands of years. But even super-Eddington accretion may not be sufficient. The earliest supermassive black holes discovered by JWST appear too massive to have formed through any accretion process, starting from stellar mass seeds. This has led to the primordial black hole hypothesis. If massive black holes formed directly from the collapse of enormous gas clouds during the universe's first seconds, they would bypass the stellar phase entirely and begin their existence with masses potentially millions of times that of our Sun. These primordial seeds would have a 400 million year head start, providing enough time to grow to the observed masses, even with conventional accretion rates. The evidence for primordial black holes is mounting. JWST has identified numerous little red dots in the early universe, compact objects with properties suggesting they might be massive black holes rather than galaxies. Some of these objects show no signs of surrounding stellar populations, appearing as isolated supermassive black holes floating in the cosmic void. This population of naked black holes cannot be explained through stellar evolution and supports scenarios where black holes formed before the first stars ignited. But primordial black holes, if they exist, raise even more disturbing questions about the universe's first moments. For gas clouds to collapse directly into black holes without forming stars requires specific conditions during the cosmic dark ages. The gas must be extremely dense, the cooling mechanisms must be inefficient enough to prevent star formation, and the collapse must proceed faster than the cosmic expansion can dilute the gas. These conditions might have been common during brief windows in the universe's early history, creating a population of massive black holes that dominated structure formation long before galaxies existed. The growth of these primordial seeds proceeded through both accretion and mergers. When two galaxies collide, their central supermassive black holes eventually spiral together and merge, creating even more massive objects. Gravitational wave observatories like LIGO and LISA have detected numerous black hole mergers, confirming that this process operates throughout cosmic history. But the merger timescales pose yet another challenge. When two supermassive black holes approach each other, they initially orbit at large distances, losing energy through gravitational wave radiation. This process is extremely slow for widely separated black holes, potentially requiring billions of years for the objects to spiral close enough to merge. Yet JWST has discovered galaxies in the early universe that show evidence of hosting dual supermassive black holes, suggesting that mergers occurred much faster than theoretical predictions. Cosmic filaments, the largest structures in the universe, are also expanding and growing. These vast chains of galaxies stretch for hundreds of millions of light years, connecting massive galaxy clusters in a network that resembles biological neural pathways. The cosmic web's architecture formed through gravitational collapse of initial density fluctuations, with matter flowing along preferred directions to create the filamentary structure we observe today. But recent observations suggest the filaments are not static. They are actively growing, both through the inflow of matter from surrounding voids and through internal processes that concentrate mass along their lengths. Wide-field galaxy surveys that map millions of galaxies have revealed that filament structures are thickening over time as additional matter accretes onto them. The rate of this thickening exceeds what simulations predict, suggesting that filament growth involves processes beyond simple gravitational collapse. One mechanism that might enhance filament growth involves magnetic fields. The cosmic web is threaded with magnetic fields of surprising strength and complexity. These fields can affect how gas flows into filaments, channeling matter along field lines and accelerating inflow velocities. Magnetic pressure can also prevent gas from dispersing once it reaches a filament, allowing the structure to maintain higher densities and attract additional matter more efficiently. If magnetic fields are stronger than current models assume, they could significantly enhance the rate at which filaments grow. Turbulence within filaments may also play a crucial role. Observations of intergalactic gas show evidence of supersonic turbulence with velocities reaching thousands of kilometers per second. This turbulence can compress gas locally, triggering star formation and galaxy assembly within the filament itself. Instead of galaxies forming first and then migrating into filaments, the filaments might be actively manufacturing galaxies through turbulence-driven collapse. This inside-out formation scenario would produce structure faster than conventional models predict. The discovery of young galaxies located within filaments supports this hypothesis. These systems show properties consistent with recent formation, suggesting they assembled in situ rather than migrating from elsewhere. If filaments are indeed forges for galaxy creation, they represent a growth mechanism that operates independently of hierarchical structure formation, building cosmic architecture through processes that have no equivalent in standard cosmology. Dark matter, the invisible scaffolding that comprises 85% of all matter in the universe, may also be growing its influence in ways we do not understand. Dark matter interacts only through gravity, creating the potential wells into which normal matter falls to form galaxies and clusters. The strength and distribution of dark matter determines how rapidly structure forms and how massive the resulting objects become. If dark matter's properties differ from our assumptions, it could dramatically affect structure formation timescales. The standard model of dark matter assumes it consists of cold, non-interacting particles that clump together solely through gravitational attraction. These particles move slowly compared to the speed of light and have no significant interactions beyond gravity. Computer simulations based on this cold dark matter paradigm reproduce the large-scale structure of the universe remarkably well, but they struggle with smaller-scale phenomena. One persistent problem involves the number of satellite galaxies around large systems like the Milky Way. Simulations predict far more small dark matter halos than we observe as actual dwarf galaxies. Either most dark matter halos failed to form visible galaxies, or the simulations are overestimating how efficiently dark matter clumps on small scales. The missing satellites problem suggests that dark matter might have properties that suppress structure formation at small scales, while enhancing it at large scales. Self-interacting dark matter represents one proposed solution. If dark matter particles can collide with each other through forces beyond gravity, these interactions would transfer momentum and heat the dark matter, preventing it from clumping too tightly in the centers of halos. This would reduce the number of small halos while leaving large-scale structure formation relatively unchanged. But if dark matter self-interactions are too strong, they would also affect the growth rate of cosmic structures, potentially slowing formation at all scales. Alternatively, dark matter might not be perfectly cold. Warm dark matter scenarios propose that dark matter particles have significant velocities, allowing them to stream out of small density fluctuations and erase structure on the smallest scales. This would explain the missing satellites while preserving the success of cold dark matter on large scales. But warm dark matter would also affect how quickly galaxies and clusters form, potentially slowing early structure formation and making it harder to explain the massive early galaxies that JWST has discovered. Fuzzy dark matter offers a more exotic alternative. In this scenario, dark matter consists of ultralight particles with properties dominated by quantum mechanics rather than classical physics. These particles have wavelengths comparable to galactic scales, creating wave-like behavior that suppresses small-scale structure while producing distinctive signatures in galaxy density profiles. Fuzzy dark matter could grow structures at different rates than conventional cold dark matter, potentially explaining some of the timing anomalies in early galaxy formation. But regardless of dark matter's exact nature, observations increasingly suggest that structures are assembling faster than our models predict. The early universe appears to have been more efficient at building galaxies, clusters, and large-scale structure than simulations based on standard cosmology can reproduce. Either initial density fluctuations were stronger than we thought, or structure formation operates through additional mechanisms we have not identified. The cosmic microwave background provides our cleanest window into initial conditions. This radiation, released when the universe was just 380,000 years old, preserves a snapshot of density fluctuations that seeded all subsequent structure. The Planck satellite mapped these fluctuations with extraordinary precision, revealing temperature variations of approximately 1 part in 100,000 across the sky. These tiny variations correspond directly to density differences in the early universe. Slightly denser regions appear as warmer spots. Slightly less dense regions appear as cooler spots. The pattern of hot and cold spots encodes crucial information about the universe's composition and initial conditions. By analyzing the statistical properties of these fluctuations, their sizes, amplitudes, and correlations, cosmologists can determine the amounts of normal matter, dark matter, and dark energy, the geometry of space, and the spectrum of initial density perturbations. This analysis has been extraordinarily successful, producing a standard cosmological model that matches multiple independent observations. But the cosmic microwave background also contains anomalies. The cold spot, a region approximately 5 degrees across that appears roughly 70 microkelvin cooler than its surroundings, represents one of the most significant deviations from predictions. Statistical analysis suggests that features this large and cold should be extremely rare, occurring in less than 2% of simulated universes. Some researchers have proposed that the cold spot results from a supervoid along that line of sight, with the Eridanus supervoid identified as a potential candidate. But even accounting for void effects, the cold spot's properties remain difficult to fully explain. The axis of evil represents another cosmic microwave background anomaly. This term describes an unexpected alignment of the largest-scale temperature fluctuations with each other and with our solar system's geometry. The quadrupole and octupole moments of the temperature distribution show correlations that should not exist if the fluctuations are truly random. These anomalies might indicate that the early universe was more complex than standard inflation models predict. Inflation, the hypothetical period of exponential expansion during the universe's first fraction of a second, should have smoothed out pre-existing irregularities and generated quantum fluctuations with specific statistical properties. Any deviation from these properties would suggest either that inflation proceeded differently than standard models describe, or that additional processes modified the fluctuations after inflation ended. Some inflation models predict that quantum fluctuations should have slight statistical asymmetries or non-Gaussian features that could produce anomalies like the cold spot and the axis of evil. If these features are confirmed as genuine cosmological signals rather than statistical flukes, they would provide crucial evidence about the physics of the ultra-early universe, potentially revealing information about quantum gravity, higher dimensions, or the properties of the inflaton field that drove cosmic expansion. But inflation itself raises questions about growth rates. The mechanism requires a scalar field, the inflaton, with potential energy that drives exponential expansion. When this field transitions to a lower energy state, the potential energy converts into matter and radiation through a process called reheating. The efficiency and speed of reheating determines the initial conditions for subsequent structure formation. If reheating proceeded more rapidly or efficiently than standard models assume, it could have created stronger initial density fluctuations, leading to faster structure formation throughout cosmic history. The nature of reheating remains poorly understood because it involves physics at energy scales far beyond what particle accelerators can probe. During reheating, the inflaton field oscillates and decays into elementary particles, transferring its energy to the quantum fields that would eventually become all the matter and radiation in the universe. If reheating was particularly violent or asymmetric, it might have created fluctuations with amplitudes larger than predicted by simple inflation models. These enhanced fluctuations would provide stronger gravitational seeds for structure formation, allowing galaxies and clusters to assemble more quickly. Some observations of early massive galaxies could be explained if the primordial power spectrum of density fluctuations had more power on certain scales than standard inflation predicts. Modified gravity theories offer an alternative explanation for accelerated structure formation. If Einstein's general relativity is not the complete description of gravity, particularly on cosmic scales, then structure might grow through mechanisms that have no equivalent in standard physics. Several modified gravity frameworks have been proposed, each suggesting different ways that gravitational physics might deviate from general relativity's predictions. Modified Newtonian dynamics, or MOND, proposes that gravity behaves differently when accelerations are extremely small. In this framework, gravitational attraction becomes stronger than Newton or Einstein predict when dealing with the tiny accelerations relevant to galaxy dynamics and cosmology. This enhanced gravity would cause structures to collapse and grow faster, potentially explaining why early galaxies appear more massive and evolved than standard cosmology allows. MOND was originally developed to explain galaxy rotation curves without invoking dark matter. Observations show that spiral galaxies rotate faster at their outer edges than visible matter can account for. Either invisible dark matter provides additional gravitational pull, or gravity itself is stronger than predicted. MOND achieves remarkable success at matching galaxy rotation curves, but it struggles with other observations, particularly gravitational lensing and the cosmic microwave background. Tensor vector scalar gravity, an extension of MOND, attempts to create a relativistic theory that recovers MOND's successes while addressing its failures. This framework introduces additional fields beyond the metric tensor of general relativity, allowing it to modify gravitational dynamics while preserving key observational successes. In TeVe's cosmology, structure formation proceeds faster than in standard models because the modified gravitational physics enhances collapse rates. Some simulations using TeVe have produced large voids and rich superclusters more readily than lambda-cold dark matter, potentially explaining the KBC void's extreme properties. F(r) gravity represents another class of modifications where the Einstein-Hilbert action is generalized to include functions of the Ricci scalar. These theories modify gravity on large scales while preserving general relativity's successes in the solar system and with binary pulsars. Different F(r) functions produce different cosmological behaviors, some of which can accelerate structure formation through effective modifications to gravitational collapse dynamics. Massive gravity theories propose that gravitons, the hypothetical particles that mediate gravitational interactions, have small but non-zero mass. This would modify gravity at cosmological distances, potentially affecting both cosmic expansion and structure formation. Some massive gravity models predict enhanced structure growth that could explain early massive galaxies without requiring unrealistic initial conditions. But all these modified gravity theories face significant challenges. They must reproduce general relativity's well-tested predictions for solar system dynamics, binary pulsar orbital decay, and gravitational wave propagation, while producing different behaviors on cosmic scales. This is a narrow target, and most modifications that enhance structure formation also predict observable deviations in other contexts that have not been detected. The most conservative explanation for faster-than-expected structure growth remains that our understanding of initial conditions is incomplete. If the primordial density fluctuations had subtly different properties than we assume, particularly more power on large scales or non-Gaussian features, this could naturally produce the observed structures without requiring new physics. The challenge is identifying which inflation models or ultra-early universe processes could generate such initial conditions while remaining consistent with all other observations. String theory, the leading candidate for a quantum theory of gravity, suggests that the early universe might have been far more complex than standard inflation models describe. String cosmology scenarios involve higher spatial dimensions, complex moduli dynamics, and phase transitions that could generate density fluctuations with unusual statistical properties. Some of these scenarios predict stronger fluctuations on the largest scales, which would seed faster growth of cosmic structures. Cosmic strings, one-dimensional topological defects that might have formed during phase transitions in the early universe, represent another potential source of enhanced structure formation. If cosmic strings existed and were sufficiently numerous, they would create wakes of enhanced density as they moved through the cosmic plasma. These wakes could seed galaxy and cluster formation more efficiently than simple density fluctuations, potentially explaining rapid structure assembly. The James Webb Space Telescope has identified several candidates for cosmic string signatures, though none have been confirmed definitively. Domain walls, two-dimensional topological defects, could produce similar effects. These structures would form if the early universe underwent a phase transition where different regions settled into different vacuum states. The boundaries between these domains would be walls of concentrated energy density that could influence structure formation. However, cosmological models with long-lived domain walls face severe constraints because such structures would dominate the universe's energy budget and create observable anisotropies that have not been detected. Primordial magnetic fields represent yet another mechanism that could enhance structure formation. If magnetic fields with strengths approaching microgauss levels existed in the early universe, they would affect how matter collapsed into the first structures. Magnetic pressure would resist collapse in some directions while enhancing it in others, potentially creating filamentary structures more efficiently than pure gravitational collapse. These primordial fields could be relics of processes during the cosmic dark ages, or might have been generated during cosmic inflation itself. The hypothesis that structure grows faster than cosmic expansion gains support from multiple independent lines of evidence. Massive early galaxies, high-velocity cluster mergers, rapidly accreting supermassive black holes, expanding voids, and thickening filaments all point toward structure formation processes that operate more efficiently than standard models predict. But these observations also force us to confront unsettling possibilities about our cosmic environment and our ability to understand it. If we live in an unusual location like the KBC void, our observations might not reflect universal properties. The Hubble tension could result from measuring expansion within an atypical region. The massive early structures JWST observes might be statistically rare outliers that happen to lie along our particular lines of sight. Our entire cosmological framework might be built on observations systematically biased by our location in a supervoid. This possibility violates the cosmological principle, the foundational assumption that the universe looks roughly the same from any vantage point once you average over sufficiently large scales. The principle has been extraordinarily successful, enabling cosmologists to model the entire universe using relatively simple mathematics. But if our location is genuinely unusual, the principle fails, and with it collapses much of our confidence in cosmological conclusions drawn from local observations. Statistical studies attempt to quantify how unusual our location would be if we truly reside in the KBC void. Computer simulations of structure formation based on standard cosmology rarely produce voids as large and deep as the KBC void. When they do, these structures represent rare statistical fluctuations, occurring in perhaps 1% to 2% of simulated universes. Finding ourselves in such a rare environment seems improbable, though not impossible. The anthropic principle offers one resolution. Perhaps observers can only arise in certain types of environments, and those environments happen to be unusual when viewed from a cosmic perspective. If galaxy formation requires specific conditions that occur preferentially in mildly underdense regions, then most observers would find themselves in modest voids, simply because that is where the conditions for life are optimal. This argument only works if the required conditions are truly rare and if they genuinely favor underdense regions, neither of which is firmly established. Alternatively, the cosmological principle might hold on scales larger than we have previously recognized. If homogeneity only emerges when averaging over a volume significantly larger than our current observable surveys, then structures like the KBC void might be common fluctuations that do not violate the principle. Future surveys that map the universe to greater depths and distances will test this possibility by determining whether large voids are as rare as current simulations suggest, or whether they represent normal variance in cosmic structure. The Baryon Oscillation Spectroscopic Survey and its successor projects have mapped millions of galaxies across billions of light-years, providing increasingly detailed pictures of large-scale structure. These surveys reveal that the cosmic web's complexity extends to the largest scales we can observe. Voids, filaments, clusters, and superclusters all appear to participate in a hierarchical organization where smaller structures merge to form larger ones, while larger structures affect the formation of smaller ones through feedback processes. But these surveys also reveal tensions with theoretical predictions. The number of massive clusters at high redshifts exceeds expectations. The scale and richness of the largest superclusters challenge formation timescales. The alignment of cosmic structure across vast distances suggests coordinated processes that have no obvious explanation in gravitational physics alone. Each of these observations hints that our models of structure formation might be incomplete in ways we have not yet identified. Gravitational lensing provides an independent probe of mass distribution that does not rely on detecting light from galaxies or gas. When massive objects like galaxy clusters bend spacetime, they deflect light from background sources, creating distorted or multiple images. The strength and geometry of this lensing directly measures the mass distribution of the foreground object, including dark matter that emits no light. Lensing surveys have mapped dark matter across cosmic volumes, revealing how it clumps and flows through the cosmic web. These lensing maps show that dark matter structure matches normal matter structure remarkably well. Galaxies and clusters form where dark matter halos are densest. Voids in the galaxy distribution coincide with voids in the dark matter distribution. This correspondence confirms that dark matter provides the gravitational scaffolding for structure formation, with normal matter flowing into the potential wells that dark matter creates. But lensing studies have also identified anomalies. Some massive clusters produce stronger lensing than their visible matter content predicts, even after accounting for expected amounts of dark matter. Either these clusters contain unusual amounts of dark matter, or the dark matter is distributed in unexpected ways. or gravitational lensing operates differently than general relativity predicts. Each possibility challenges standard assumptions and suggests that the relationship between visible matter, dark matter, and gravity might be more complex than current models assume. Weak lensing, where the distortions are too subtle to create multiple images but can be detected statistically across many background galaxies, provides even broader probes of mass distribution. These studies map the cosmic web's dark matter structure across vast volumes, revealing how matter organizes on the largest scales. Recent weak lensing surveys have found evidence for underdense regions and overdense regions larger than standard cosmology predicts, supporting the idea that structure formation proceeds more efficiently than expected. The growth of structure couples intimately with cosmic expansion through the competition between gravity and dark energy. In dense regions, gravity pulls matter together, resisting the expansion and potentially even causing local contraction. In underdense regions, dark energy dominates, accelerating the expansion and causing voids to grow faster than the cosmic average. This competition creates the intricate cosmic web structure we observe, with its mix of dense filaments and empty voids. But the balance between gravity and dark energy might be shifting over cosmic time. Dark energy appears to be constant in density even as space expands, meaning its total energy content grows while matter's energy content remains fixed. In the early universe, matter dominated and gravity controlled structure formation. As the universe expanded and aged, dark energy became increasingly important, eventually dominating the cosmic energy budget approximately 5 billion years ago. This transition from matter domination to dark energy domination marks a fundamental shift in cosmic evolution. Before the transition, structure formation proceeded efficiently as gravity pulled matter into increasingly massive systems. After the transition, dark energy began inhibiting collapse, preventing new large-scale structures from forming and causing existing voids to expand ever more rapidly. The universe's architecture effectively froze in place, with further evolution limited to the merger and rearrangement of existing structures, rather than the creation of fundamentally new organization. The timing of this transition affects how massive the largest structures can become, and how empty the largest voids can grow. If dark energy became important earlier than we think, it would have shut down structure formation sooner, preventing the most massive clusters from assembling and keeping voids smaller. If dark energy became important later, larger structures could have formed and voids could have grown to greater sizes. Evidence from the largest known structures suggests that dark energy's influence might have been weaker in the past than in the present. Superstructures like the Sloan Great Wall, stretching 1.37 billion light-years, should be extremely rare if dark energy has always had its current strength. Their existence hints that structure formation had a longer period to operate before dark energy shut it down, which would require either that dark energy was weaker early on or that initial density fluctuations were stronger than we assume. Evolving dark energy represents one proposed solution. If dark energy's density changes over time rather than remaining constant, it could explain several cosmological anomalies simultaneously. Models where dark energy was weaker in the past and strengthened over time would allow more vigorous structure formation early on while producing the accelerated expansion we observe today. This scenario could explain massive early galaxies, large superstructures, and the current expansion rate without requiring statistically unlikely initial conditions or unusual observer locations. But evolving dark energy faces significant theoretical challenges. The simplest form of dark energy, Einstein's cosmological constant, is rigorously constant by definition. Making dark energy evolve requires introducing new fields or modifying the vacuum energy properties in ways that lack compelling theoretical motivation. Quantum field theory predicts a vacuum energy density approximately 120 orders of magnitude larger than the observed dark energy density, one of the most spectacular failures in theoretical physics. Any successful model of evolving dark energy must explain not only why dark energy has its observed small value, but also why that value would change over cosmic time. Quintessence models attempt to address these issues by proposing that dark energy arises from a dynamical scalar field rather than vacuum energy. This quintessence field evolves over time as it rolls down a potential energy curve, causing its energy density and equation of state to change. Different potentials produce different evolution histories, some of which might explain observational anomalies. But quintessence models face their own fine-tuning problems. requiring potential shapes that produce both the current acceleration and the past deceleration without introducing observable instabilities or conflicts with other measurements. The growth rate of cosmic structure provides one of the strongest tests of dark energy properties. In standard cosmology with a cosmological constant, structure growth follows specific mathematical predictions that depend only on the matter density and expansion rate. Measurements of how clustering strength increases over time test whether these predictions hold. Deviations would indicate either that dark energy evolves or that gravity operates differently than general relativity describes. Current measurements show tantalizing hints of deviations. Some clustering studies find that structure grows slightly faster than lambda-cold dark matter predicts, particularly at recent cosmic epochs. These results are not yet statistically definitive, but they suggest that either dark energy is weaker than the cosmological constant or gravity is slightly stronger than general relativity predicts on large scales. Either possibility would have profound implications for cosmic evolution and the fate of structure in the far future. The fate of cosmic structure depends critically on dark energy's behavior. If dark energy remains constant, the universe's expansion will accelerate forever. Cosmic structures that are not already gravitationally bound will separate and lose causal contact. Voids will expand to consume ever larger fractions of the total volume. Galaxy clusters will become isolated islands in an expanding ocean of emptiness. Star formation will gradually cease as gas is exhausted or expelled. The universe will enter a long twilight phase where existing stars slowly burn out while no new ones form to replace them. On timescales of trillions of years, even gravitationally bound structures will eventually evaporate through gravitational interactions that eject stars into the intergalactic void. Galaxies will become increasingly diffuse. Clusters will disperse. Eventually, even atoms might decay if protons are unstable, a possibility suggested by some grand unified theories. The universe's ultimate fate under constant dark energy is a cold, dark, nearly empty expanse with a few scattered black holes as the last remaining concentrations of energy and information. But if dark energy strengthens over time, the fate becomes more dramatic. In the Big Rip scenario, dark energy's repulsive pressure increases until it overcomes not just cosmic expansion, but also the gravitational binding of galaxies, stars, planets, molecules, and eventually atoms themselves. This catastrophic end would occur on finite timescales, potentially in just tens of billions of years. Galaxies would be torn apart first as dark energy overcomes their gravitational binding. Solar systems would dissolve as planets are ripped from their orbits. Stars would explode as their self-gravity loses to dark energy's pull. Finally, atoms would be shredded as electromagnetic forces fail to hold electrons to nuclei against the exponentially growing space expansion. The Big Rip requires dark energy with an equation of state parameter less than -1, corresponding to vacuum energy that grows denser as space expands. This violates several energy conditions in general relativity and requires exotic forms of matter or modifications to gravitational physics. Current observations constrain the equation of state parameter to be very close to -1, the value for a cosmological constant, but do not definitively rule out phantom energy that could lead to a Big Rip. Vacuum decay represents an even more terrifying possibility. Quantum field theory suggests that our universe's vacuum state might not be the true minimum energy configuration. Instead, we might exist in a metastable false vacuum that will eventually transition to a lower energy true vacuum through quantum tunneling. When this transition occurs, it would create an expanding bubble of true vacuum that converts all matter and energy into new configurations with different physical constants and particle properties. This bubble would expand at the speed of light, giving no warning before it arrives. Everything inside would be destroyed and reconfigured according to the true vacuum's physics. The probability of vacuum decay depends on parameters we cannot measure directly. Some calculations suggest our vacuum is stable and will persist forever. Others indicate metastability with decay timescales far longer than the current age of the universe. But some scenarios allow vacuum decay on cosmologically short timescales. If we are unlucky, vacuum decay could be triggered by high-energy particle collisions, strong gravitational fields near black holes, or random quantum fluctuations. There would be no defense and no survival. The bubble wall would simply erase everything it encountered, replacing our universe with something fundamentally alien. These apocalyptic scenarios remain speculative, but they illustrate the profound uncertainties that persist in our understanding of dark energy and cosmic fate. We do not know what dark energy is. We do not know whether it is constant or evolving. We do not know whether our vacuum state is stable. These gaps in knowledge mean we cannot confidently predict the universe's ultimate destiny or the timescales on which current cosmic structures will persist. What we can observe is that structures are growing and evolving now, through processes that challenge our models and force us to question our assumptions. The universe is not simply coasting along in predictable expansion. It is actively assembling architecture on the largest scales through mechanisms we do not fully understand. And some of these mechanisms appear to operate faster than the expansion of space itself, creating structures that defy our theoretical expectations. The cosmic web is the universe's skeleton, the framework upon which all other structures hang. Its formation through gravitational collapse of primordial density fluctuations represents one of cosmology's great successes. Computer simulations reproduce the web's basic architecture remarkably well, creating virtual universes that look convincingly similar to the real cosmos when viewed at large scales. But these successes exist alongside persistent failures and anomalies that suggest our understanding remains incomplete. One persistent problem involves the web's morphology. Observations show that filaments have a characteristic thickness and density profile that simulations struggle to reproduce precisely. Real filaments appear to be slightly thicker and denser than simulations predict, suggesting that some physical process is enhancing their growth beyond simple gravitational collapse. Candidate mechanisms include magnetic fields, turbulence, early energy injection from supernovae or active galactic nuclei, or systematic errors in how we measure filament properties from observations. The alignment of structures within the cosmic web also poses challenges. Galaxies within filaments tend to align with the filament direction, their angular momentum vectors showing statistical correlations with the large-scale structure. This alignment should result from tidal torques generated by the gravitational field of the surrounding mass distribution. But the strength and persistence of these alignments exceed what simulations predict, suggesting that the tidal field is stronger or operates more efficiently than models assume. Correlations extend even farther. Galaxy cluster orientations show correlations across distances exceeding 100 megaparsecs, far larger than the scales over which gravitational interactions should create coherent alignments. These long-range correlations might indicate that the initial density field had non-Gaussian features that seeded correlations on very large scales. Alternatively, they might result from processes during structure formation that we have not identified, perhaps related to magnetic fields or cosmic flows on scales exceeding our simulation volumes. The velocity structure of the cosmic web also contains surprises. Galaxies and clusters participate in large-scale flows called bulk flows, where entire regions of space move coherently in particular directions. The local group is falling toward the Virgo cluster at approximately 600 kilometers per second, but Virgo itself is falling toward an even more massive concentration called the Great Attractor. And the Great Attractor participates in a still larger flow toward the Shapley supercluster. These nested flows reveal a hierarchical velocity structure that extends to the largest scales we can measure. Bulk flow measurements show systematic velocities that exceed predictions from standard cosmology. When averaged over volumes hundreds of megaparsecs across, the coherent motions should largely cancel out, approaching zero in the limit of very large volumes. But observations continue to show significant bulk flows even on scales where they should have vanished. Either we are measuring incorrectly, we occupy an unusual location with atypical velocity structure, or the cosmic web has more large-scale velocity coherence than models predict. The Great Attractor itself remains partially mysterious despite decades of study. This gravitational anomaly, located approximately 250 million light-years away in the direction of the Hydra and Centaurus constellations, appears to be pulling our local group and numerous other galaxies toward it. But its nature has been difficult to determine because it lies in the zone of avoidance, a region obscured by the Milky Way's dust and stars. X-ray and infrared observations that penetrate the dust have revealed that the Great Attractor region contains the Norma cluster and other massive structures, but the total mass remains uncertain. Beyond the Great Attractor lies the Shapley supercluster, an even more massive concentration containing over 8,000 galaxies. Shapley's gravitational influence extends across hundreds of millions of light-years, affecting the motion of everything in its vicinity, including the Great Attractor itself. This hierarchy of attractors suggests that mass is distributed in nested concentrations extending to the largest observable scales, with each level of structure participating in flows towards still larger concentrations. These flows challenge the cosmological principle because they indicate preferred directions in the universe's velocity field. If observers at vastly different locations all measure similar bulk flows pointing in the same direction, it suggests that the universe has large-scale organization that violates statistical isotropy. Current observations have not definitively established such violations, but they hint that the velocity field might have more structure than simple homogeneous expansion predicts. The Hubble tension connects directly to these issues. If we measure the expansion rate within a region participating in bulk flows, our measurement includes both the cosmic expansion and the peculiar velocity contribution from the flows. Disentangling these components requires precise distance measurements that do not rely on redshift, which mixes expansion and peculiar velocity indistinguishably. Techniques like Tully-Fisher relations and tip-of-the-red giant branch measurements provide such distance estimates, but they have larger uncertainties than redshift-based methods, limiting how precisely we can separate cosmic expansion from local flows. The KBC void's expansion contributes to these bulk flows. Matter within the void flows outward toward the denser regions beyond its boundaries, creating systematic velocities that affect our measurements of the Hubble constant. If we use nearby supernovae to measure expansion, we are necessarily sampling galaxies within the void that participate in these outflows. This adds a positive bias to our measurement, making the expansion appear faster than the true cosmic average. Correcting for the void's influence requires detailed modeling of its density profile and velocity field, but these properties are not precisely known. Different observational techniques give somewhat different measurements of the void's depth and extent. The correction factor depends sensitively on these parameters, introducing systematic uncertainties that are difficult to quantify. Until we have better maps of the void's three-dimensional structure, the correction remains uncertain and the Hubble tension persists. Even with perfect knowledge of our local environment, a deeper question remains. Why does the universe have voids as large as the KBC void in the first place? Standard cosmology predicts a range of void sizes based on the statistical properties of initial density fluctuations. But the KBC void appears to sit at the extreme tail of this distribution. Simulations produce voids this large in less than 1% of realizations. Finding ourselves in such a rare structure seems improbable unless we misunderstand either the statistics of structure formation or the mechanisms that create voids. Modified gravity theories that enhance structure formation typically produce larger voids more frequently than standard cosmology. By strengthening gravitational collapse in overdense regions, these theories also create deeper and more extensive underdensities in the corresponding voids. Some modified Newtonian dynamics simulations naturally produce voids approaching the KBC void size without requiring unusual initial conditions. This provides circumstantial evidence for modified gravity, though not definitive proof. Primordial non-Gaussianity represents another possible explanation. If the initial density fluctuations had statistical properties beyond simple Gaussian random noise, the distribution of structure sizes and amplitudes would differ from standard predictions. Certain types of non-Gaussianity enhance the probability of large-scale structures, including both massive clusters and deep voids. Future cosmic microwave background missions and large-scale structure surveys will place increasingly stringent constraints on non-Gaussianity, testing whether this explanation can account for the observed structures. The puzzle of faster-than-expansion growth might ultimately require accepting that the universe is more complex and diverse than our models assume. Perhaps structure formation does not follow a single universal pattern but varies depending on local conditions in ways we have not yet discovered. Perhaps the early universe had regions with different properties, creating islands of enhanced or suppressed structure formation. Perhaps the cosmic web itself is alive with processes we have barely glimpsed, mechanisms that operate on scales so vast that we cannot directly observe them unfolding. What remains certain is that observation continues to challenge theory. Every new survey reveals structures at the limits of what cosmology predicts. Every improvement in measurement precision uncovers tensions between different observational methods. The universe we observe is richer, stranger, and more dynamic than the simple expanding cosmos described in textbooks. And somewhere within this complexity, processes are operating that build structure faster than space itself expands, creating an architecture of matter and energy that defies our attempts to explain it. Our cosmic neighborhood might be exceptional. We might occupy a statistical outlier, a rare bubble in an otherwise ordinary universe. Or we might be witnessing universal processes that appear unusual only because our models are incomplete, our measurements are imperfect, or our theoretical frameworks miss crucial physics. Distinguishing between these possibilities requires observations of unprecedented precision across cosmic volumes, larger than we have yet surveyed. The coming generation of telescopes and surveys will provide crucial tests. The Rubin Observatory will map tens of billions of galaxies, creating three-dimensional maps of cosmic structure extending billions of light-years in every direction. The Euclid Space Telescope will perform complementary surveys, measuring galaxy shapes and positions with exquisite precision to map dark matter through gravitational lensing. The James Webb Space Telescope continues to probe the early universe, discovering galaxies and black holes at ever-increasing redshifts and testing our models of how structure formed in cosmic dawn. These observations will either confirm that we live in unusual surroundings, or reveal that rapid structure growth is common throughout the cosmos. They will measure whether dark energy evolves or remains constant. They will determine whether gravity operates according to general relativity on all scales or requires modifications. They will constrain the properties of dark matter and test whether it interacts through forces beyond gravity. Each result will narrow the space of viable cosmological models, pushing us toward a more complete and accurate understanding of how the universe truly works. But regardless of what these future observations reveal, we are confronted now with phenomena that exceed our current explanations. Voids expanding faster than cosmic averages, black holes growing faster than accretion physics allows, galaxies assembling faster than merger timescales permit, filaments thickening faster than simulations predict, structures aligning across distances exceeding gravitational causality. Each observation whispers that our cosmos operates according to principles we have not yet grasped, following mechanisms we have not yet identified, building architecture through processes we have not yet understood. The universe is not simply expanding, it is organizing itself into structures of breathtaking complexity and scale. And some of these structures are growing so rapidly that they outpace even the expansion of space itself, creating concentrations of matter and energy that should not exist according to our best theories. We are witnessing cosmic evolution in real time. The galaxies we observe are falling into clusters. The clusters are merging into superclusters. The voids are expanding and pushing matter into filaments. This evolution proceeds through gravity, dark matter, dark energy, and perhaps forces we have not discovered. It is not a static picture but a dynamic process that continues around us, reshaping the cosmos on timescales both longer and shorter than we imagined. And we are part of this process. Every atom in your body was forged in stars that participated in this cosmic evolution. The calcium in your bones came from supernovae that detonated within ancient galaxies that themselves formed through the collapse of primordial density fluctuations. The carbon that makes up your DNA was synthesized in stellar cores that burned for billions of years before explosive deaths scattered their ashes across space. You are made of stardust that has witnessed cosmic history, carried along by flows and currents that operate on scales beyond human imagination. But you are also temporary. The structures that birthed you are themselves temporary, destined to disperse and evolve as the universe ages. The Milky Way will merge with Andromeda in approximately 4 billion years. Our local group will eventually fall into the Virgo cluster. That cluster will merge with others to form even larger structures. Or perhaps dark energy will tear everything apart, isolating each galaxy in its own cosmic horizon, severing all connections and making the universe an archipelago of light islands surrounded by endless expanding darkness. The timescales are vast, but not infinite. Everything that grows must eventually decay. Every structure that assembles will ultimately disperse. The second law of thermodynamics guarantees that entropy increases, order dissolves, and complexity gives way to simplicity. The cosmic web that currently organizes the universe will fade as stars die, galaxies evaporate, and black holes slowly radiate away their mass through Hawking radiation. In the inconceivably distant future, only a thin gruel of elementary particles will remain, spread across a space that expands forever, accelerating into cold and silent darkness. But that future remains trillions of years away. For now, the universe builds, matter concentrates, gravity operates, stars ignite. And somewhere within this vast cosmic construction project, processes are unfolding that move faster than space itself expands, creating structures that challenge our understanding and force us to confront the limits of our knowledge. We are observers perched on a small planet, using instruments of remarkable sophistication to probe the cosmos around us. But our view is limited by distance, by time, by the speed of light, and by the fundamental opacity of dark matter and dark energy. We see only a fraction of what exists, we understand only a fraction of what we see, and we are only beginning to grasp that some cosmic processes operate at speeds that exceed even the expansion that carries galaxies across the cosmos. Something is growing faster than space itself. This is not speculation, this is observation. These structures exist, their growth rates are measurable. Their properties challenge our theories. Whether they result from unusual initial conditions, modified physics, or processes we have never imagined, they force us to acknowledge that the universe contains mechanisms that operate beyond our current understanding, building architecture through pathways we are only now beginning to glimpse. The cosmos is vast, ancient, and largely indifferent to human concerns. But it is also magnificent in its complexity, beautiful in its organization, and humbling in its scale. Every new discovery reveals depths we had not suspected. Every observation constrains possibilities while opening new questions. The universe rewards curiosity while punishing hubris, offering glimpses of truth to those patient and careful enough to look, while reminding us constantly of how much remains unknown. We stand at a threshold. Our instruments have reached the sensitivity to detect cosmic-scale anomalies. Our theories have developed the sophistication to make precise predictions. The gap between prediction and observation has never been clearer. What we do with this knowledge, how we respond to these challenges, will determine whether the current generation marks a turning point in our cosmic understanding or merely another chapter in the long history of puzzlement and mystery. The structures growing faster than space are calling to us. They are data points demanding explanation. They are puzzles requiring solution. They are windows into physics we do not yet comprehend. What they will ultimately reveal about the cosmos, about its origins, about its fate, remains uncertain. But their existence is undeniable. And their challenge to our understanding is absolute. If you've journeyed this far through cosmic scales beyond comprehension, if you've witnessed structures that defy the very expansion that should contain them, if you felt the vertigo of realizing our models might be catastrophically incomplete, then you understand what is at stake. This is not academic curiosity. This is the universe screaming at us that we do not yet understand how it works. Hit that like button. Subscribe to this channel, because what comes next will make everything we've discussed seem simple by comparison. The universe does not care about our models. It operates according to its own logic, indifferent to whether our equations can describe its behavior. And now, as we peer deeper into the mechanisms driving structure growth, we are discovering that the forces shaping cosmic architecture might be fundamentally different from what we assumed. The question is not just what is growing faster than space itself, the question is why anything can grow faster than expansion at all. Dark energy dominates approximately 68% of the universe's total energy budget. This mysterious component drives cosmic acceleration, pushing space apart at an ever-increasing rate. In regions where matter is sparse, dark energy should completely control dynamics, preventing any process from overcoming the expansion and building structure. Yet we observe exactly the opposite. Voids expand faster than average, yes, but they also develop internal structure. Filaments thread through them. Isolated galaxy groups persist within them. And these structures show evidence of ongoing growth through processes that should have been shut down billions of years ago. The contradiction runs deeper when we examine the math. The Friedmann equations, derived from general relativity, govern cosmic expansion. They specify precisely how the universe's scale factor evolves over time based on its matter, radiation, and dark energy content. These equations work extraordinarily well at describing the global expansion history from the Big Bang to the present, but they assume homogeneity and isotropy, treating the universe as perfectly smooth when averaged over large scales. Real structure violates these assumptions. In regions denser than average, the local expansion rate should be slower than the cosmic mean. Gravity from the excess matter pulls inward, resisting expansion and potentially causing local contraction even while the universe as a whole expands. This is why galaxy clusters remain bound despite cosmic expansion. Their self-gravity overcomes the expansion on local scales, allowing them to collapse and virialize into stable systems. In regions less dense than average, the opposite should occur. With less matter to resist expansion, these underdense regions should expand faster than the cosmic mean. But there is a limit. The expansion rate in a void should be determined by the sum of the cosmic expansion, plus an additional contribution from the density deficit. Standard calculations suggest this additional contribution should be at most 10% to 15% for typical voids. The KBC void breaks this limit. Velocity measurements indicate expansion rates exceeding the cosmic mean by 30% to 40%. Either the void is far deeper than our measurements indicate, approaching a 40% density deficit instead of 20%, or some mechanism beyond simple gravitational dynamics is amplifying the expansion. Both possibilities challenge our understanding. If the void is truly 40% underdense, it becomes even more statistically improbable. The likelihood of such a deep void forming through random density fluctuations drops to perhaps 1 in 10,000 or less. We would be occupying an environment so unusual that virtually no other observers in the observable universe would experience similar conditions. This seems to violate the mediocrity principle, the idea that our location and circumstances should be typical rather than exceptional. Alternatively, if the void is 20% underdense as most measurements suggest, then its enhanced expansion requires new physics. Screened modified gravity theories offer one possibility. In these frameworks, gravity behaves normally in high-density environments like the solar system, but modifies in low-density regions like voids. The screening mechanism suppresses deviations from general relativity, where the theory has been tested, while allowing significant modifications in precisely those environments where tests are difficult. Some screened gravity theories predict void expansion rates matching the KBC void's observed behavior. Chameleon mechanisms represent one implementation of screening. In these theories, a scalar field couples to matter, with a strength that depends on local density. In high-density environments, the field acquires a large effective mass, making its range extremely short and suppressing its influence. In low-density environments, the field's effective mass drops, extending its range and allowing it to modify gravitational dynamics. The result is a theory that passes solar system tests while producing enhanced void expansion. Symmetron mechanisms work similarly, but with different density dependence. The scalar field's coupling to matter turns on in low-density regions and turns off in high-density regions through a symmetry-breaking mechanism. This creates a sharp transition between general relativity behavior and modified gravity behavior at a critical density threshold. If voids like the KBC void fall below this threshold, they would experience dramatically different expansion dynamics than standard cosmology predicts. Weinstein screening uses a different approach, invoking nonlinear field interactions rather than density-dependent couplings. Near massive objects, nonlinear terms in the field equations become important, suppressing modifications to gravity. Far from massive objects, the nonlinear terms become negligible, and modifications emerge. This mechanism appears naturally in massive gravity theories and certain higher-dimensional models, providing a theoretical framework for enhanced void expansion. But all screened gravity theories face significant challenges. They must be carefully constructed to avoid observational conflicts in multiple domains simultaneously. They must pass solar system tests, binary pulsar constraints, cosmological structure formation requirements, and cosmic microwave background observations. The parameter space where all constraints are satisfied is narrow, and many proposed models have been ruled out by increasingly precise observations. Testing these theories requires measurements in precisely the environments where screening is weakest, namely the interiors of cosmic voids. This is extraordinarily difficult because voids contain few galaxies to serve as test particles. The handful of void galaxies that do exist are typically faint dwarfs that are challenging to observe and characterize. Measuring their velocities precisely enough to constrain void dynamics requires extensive observational campaigns with the largest telescopes. The few studies that have attempted such measurements find tantalizing hints of enhanced expansion in the largest voids, but the uncertainties remain large. distinguishing a 15% expansion enhancement predicted by standard cosmology from a 35% enhancement predicted by some modified gravity theories, requires velocity measurements accurate to better than a few percent. Achieving such precision for faint distant galaxies pushes current observational capabilities to their limits. Gravitational lensing offers an alternative probe. Light passing through voids should be deflected by the mass distribution within them, creating subtle but measurable distortions in background galaxy shapes. The strength of this lensing depends on the void's integrated mass along the line of sight, which in turn depends on both the density profile and the gravitational theory governing light deflection. Modified gravity theories predict different lensing signatures than general relativity for the same matter distribution. Stacking techniques that combine weak lensing signals from hundreds or thousands of voids have begun to detect the predicted signals. Early results show that voids do create measurable gravitational lensing consistent with their containing approximately 20% less matter than average. But the precision is not yet sufficient to distinguish between general relativity and modified gravity predictions. Future surveys with better statistics and reduced systematic errors will provide crucial tests. The integrated Sachs-Wolf effect provides yet another probe. Cosmic microwave background photons passing through evolving gravitational potentials experience temperature shifts as they fall into and climb out of potential wells. In a static universe, these shifts would cancel exactly. But in an expanding universe with evolving structure, the cancellation is imperfect, leaving a net temperature change. Voids create cold spots in the cosmic microwave background through this effect, with the temperature deficit depending on how rapidly the void expands. Observations confirm that large voids create detectable cold spots in the cosmic microwave background. The statistical detection is robust, though individual void cold spot associations remain uncertain due to projection effects and the large size of cosmic microwave background features. The measured temperature deficits roughly match standard cosmology predictions, but the uncertainties are large enough that enhanced void expansion cannot be ruled out. Higher resolution cosmic microwave background measurements and better void catalogs will refine these tests. Each of these observational probes provides an independent constraint on void dynamics and gravitational physics. When combined, they paint an increasingly detailed picture of how voids evolve and whether their expansion matches theoretical predictions. The emerging consensus suggests that most voids behave roughly as expected, expanding slightly faster than the cosmic mean in accordance with their density deficits. But the largest voids, particularly supervoids like the KBC void and the Eridanus supervoid, show hints of enhanced expansion that may require either deeper density deficits than direct measurements indicate, or modifications to gravitational physics. The supermassive black hole growth problem presents a parallel challenge. These objects require time to accumulate their enormous masses through accretion and mergers. The standard formation scenario begins with stellar mass black holes formed from the deaths of the first massive stars. These seed black holes then grow through gas accretion, gaining mass exponentially if they can maintain sustained feeding. Mergers with other black holes provide additional growth, particularly during galaxy mergers that bring two supermassive black holes into proximity. The exponential growth timescale depends critically on the accretion rate. At the Eddington limit, a black hole can double its mass in approximately 50 million years. Starting from a 100 solar mass stellar black hole, reaching a billion solar masses requires approximately 23 doubling times, or roughly 1.15 billion years of continuous Eddington-limited accretion. This calculation assumes perfect efficiency with no interruptions in feeding, which is almost certainly unrealistic. Real black hole growth occurs episodically. Galaxies experience periods of active feeding when gas-rich mergers or other processes funnel large quantities of material toward the central black hole. These active phases, visible as quasars or active galactic nuclei, can last millions to tens of millions of years. Between active phases, black holes enter quiescent periods with minimal accretion. The duty cycle, the fraction of time spent in active feeding, significantly affects the average growth rate. If black holes spend only 10% of their time actively accreting, then growing from stellar mass to a billion solar masses requires not 1.15 billion years, but 11.5 billion years. This is barely acceptable given that the universe is 13.8 billion years old, and it leaves no margin for the time required for the first stars to form and die. Yet JWST has discovered billion solar mass black holes existing just 400 million years after the Big Bang, when the universe was less than 3% of its current age. The math simply does not work using standard assumptions. Either these black holes are accreting far faster than the Eddington limit for sustained periods, or they started from seed masses far larger than stellar black holes, or both. The discovery of black holes like LID 568 accreting at 40 times the Eddington limit demonstrates that super-Eddington accretion is possible, at least temporarily. But sustaining such extreme feeding rates for millions of years requires conditions we do not understand. One possibility involves optically thick accretion flows where radiation becomes trapped in the infalling matter. In standard thin disk accretion, radiation escapes freely, creating the pressure that enforces the Eddington limit. But if the accretion rate is high enough, the flow becomes optically thick, trapping radiation within the gas. This allows matter to fall inward despite the enormous radiation energy being generated, potentially permitting super-Eddington accretion rates. Simulations of super-Eddington accretion show complex behavior. The disk puffs up into a thick torus, with jets and outflows carrying away excess energy and angular momentum. The geometry becomes highly non-spherical, with funnel-shaped inflow regions along the rotation axis and powerful winds blowing away matter in other directions. The net accretion rate onto the black hole can exceed the Eddington limit, but much of the infalling material is redirected into outflows rather than crossing the event horizon. The efficiency of super-Eddington accretion depends on magnetic fields, viscosity, radiation transfer, and gas thermodynamics in ways that are difficult to model accurately. Three-dimensional, general relativistic magnetohydrodynamic simulations are required to capture the relevant physics, and even these simulations must make approximations that introduce uncertainties. Current models suggest that sustained super-Eddington accretion by factors of 10 to 100 might be possible under certain conditions, but the parameter space where such accretion occurs remains poorly mapped. Even with super-Eddington accretion, the seed mass problem persists. Starting from 100 solar mass seeds and accreting at 40 times the Eddington limit reduces the growth timescale by a factor of 40. Allowing billion solar mass black holes to form in approximately 30 million years. But this extreme scenario requires both sustained super-Eddington accretion and an abundant gas supply to feed the black hole continuously. Whether such conditions existed in the early universe remains uncertain. Direct collapse black holes offer a radical alternative. If sufficiently massive gas clouds can collapse directly into black holes without forming stars, they would provide seed masses of 10,000 to 1,000,000 solar masses. These heavy seeds would require far less subsequent growth to reach the billion solar mass black holes observed at high redshift. Starting from a 100,000 solar mass seed, even standard Eddington limited accretion could produce a billion solar mass black hole in approximately 350 million years, making the early quasars comprehensible. But direct collapse requires very specific conditions. The gas cloud must be massive enough that its self-gravity overcomes pressure support, typically requiring masses exceeding 100,000 solar masses. The gas must remain molecular hydrogen-free because molecular hydrogen provides efficient cooling that would fragment the cloud and trigger normal star formation. Radiation from nearby young galaxies can dissociate molecular hydrogen, creating the required conditions. But this requires a delicate balance. Enough nearby star formation to provide the dissociating radiation, but not so much that heavy elements from supernovae contaminate the gas and trigger fragmentation. Primordial black holes formed in the first seconds after the Big Bang represent the most exotic seed scenario. During this ultra-early epoch, density fluctuations might have been large enough on small scales to collapse directly into black holes. These primordial black holes would have formed before the first atoms, before the first stars, providing seeds that existed from essentially the beginning of cosmic time. The mass spectrum of primordial black holes depends on the conditions during the collapse epoch. Standard inflation models predict that primordial black holes should be extremely rare, with masses clustered around micrograms to grams. Such tiny black holes would evaporate through Hawking radiation long before the present day. But non-standard inflation scenarios or phase transitions in the early universe might produce primordial black holes with masses ranging from stellar to millions of solar masses. If primordial black holes with masses of thousands to millions of solar masses existed, they would provide ideal seeds for supermassive black hole formation. They would be sitting in the first dark matter halos when gas began cooling and falling inward, perfectly positioned to accrete efficiently and grow rapidly. By the time the first stars formed, these primordial black holes could already have reached intermediate masses, giving them a substantial head start in the race to become supermassive. Evidence for primordial black holes remains circumstantial. The little red dots discovered by JWST show properties consistent with massive black holes, but confirming their nature requires detailed spectroscopic follow-up that is ongoing. Some of these objects appear unusually compact and massive for their redshift, suggesting they might be black holes rather than galaxies. If confirmed, they would provide strong evidence that massive black holes existed very early, potentially supporting primordial formation scenarios. The existence of naked black holes like QSOJH plus 09 adds another piece of the puzzle. This object appears to be a supermassive black hole with minimal surrounding stellar population, sitting isolated in the early universe. How such an object could form without simultaneously building a galaxy around it remains mysterious. Primordial black holes would naturally be naked initially, accreting gas directly without building substantial stellar populations until later epochs. Regardless of their formation mechanism, supermassive black holes clearly grow faster than standard accretion theory predicts. Whether through super-Eddington accretion, heavy seeds, primordial origins, or some combination of mechanisms, these objects achieve their enormous masses in times far shorter than simple calculations suggest possible. They are growing faster than the cosmic expansion can dilute their food supply, concentrating mass at rates that challenge our physical models. Galaxy formation itself shows evidence of accelerated timescales. The massive early galaxies discovered by JWST should not exist according to standard hierarchical formation models. These frameworks predict that galaxies build up gradually through mergers of smaller systems over billions of years. Small galaxies form first from the collapse of the smallest dark matter halos. These merge to form larger galaxies, which merge to form still larger systems in a bottom-up assembly process. The merger timescale depends on the orbital period and dynamical friction timescale for the merging systems. Two galaxies on a collision course will take multiple orbital periods to merge fully as dynamical friction drains their orbital energy. For massive halos separated by typical distances, the merger timescale is hundreds of millions to billions of years. Building a Milky Way mass galaxy through this process requires multiple merger generations, extending the total formation time to several billion years. Yet, JWST has found galaxies with stellar masses approaching 100 billion solar masses existing just 500 million years after the Big Bang. These systems contain as many stars as our Milky Way, but formed in 1/26th the time. Their stellar populations show evidence of being relatively old, suggesting star formation began even earlier, perhaps 200 to 300 million years after the Big Bang. The universe would have been less than 2% of its current age. Building such massive galaxies so quickly requires either extremely efficient star formation or a formation mechanism entirely different from hierarchical assembly. Star formation efficiency measures what fraction of available gas gets converted into stars. In the local universe, efficiency is typically 1% to 10%. Most gas is blown away by supernovae and stellar winds or heated too hot to collapse. Achieving high stellar masses quickly requires either much higher efficiency approaching 50% to 100% or vastly larger gas reservoirs than standard models predict. Some simulations of early galaxy formation suggest that conditions in the high-density early universe might have permitted higher star formation efficiencies. The cosmic microwave background radiation was hotter, providing a floor temperature that suppressed fragmentation and allowed gas clouds to collapse into more massive stars. Higher gas densities increased collision rates and promoted rapid accretion onto protostars. These effects could boost star formation efficiency above local universe values. But even maximally efficient star formation struggles to explain the most massive early galaxies. Converting all available gas into stars at the highest physically plausible rates still requires several hundred million years to build a 100 billion solar mass galaxy. The most extreme JWST discoveries formed in half that time or less, suggesting that star formation efficiency alone cannot explain them. Direct collapse of gas into stellar clusters offers an alternative. If giant molecular clouds in the early universe were sufficiently massive and dense, they might collapse directly into bound stellar clusters containing millions to billions of stars in single events. This would bypass the gradual bottom-up assembly process, creating massive stellar systems almost instantaneously on cosmic timescales. Evidence for such direct collapse is limited, but some of the compact early galaxies discovered by JWST show properties that might be consistent with this scenario. The role of dark matter in early galaxy formation adds another layer of complexity. Dark matter halos provide the gravitational potential wells into which gas falls to form galaxies. The rate at which halos grow through accretion and mergers determines how quickly galaxy formation can proceed. Standard cold dark matter produces a well-defined halo mass function that specifies how many halos of each mass exist at different cosmic epochs. But if dark matter has properties beyond the standard cold, non-interacting paradigm, halo growth rates could differ significantly. Warm dark matter with significant velocities would suppress small-scale structure, reducing the number of low-mass halos available to merge into larger systems. This would slow hierarchical assembly. Self-interacting dark matter with frequent collisions would modify halo density profiles, potentially affecting how efficiently gas cools and forms stars. Fuzzy dark matter with quantum properties would create wave-like interference patterns that could either enhance or suppress structure formation depending on scale. Current observations do not definitively favor any of these exotic dark matter scenarios over standard cold dark matter. But they also do not rule them out. The parameter space for dark matter properties remains large, and different choices within that space can produce dramatically different predictions for early galaxy formation. If dark matter turns out to have unexpected properties, it might explain some of the massive early galaxies while simultaneously creating new puzzles in other domains. Primordial magnetic fields represent another potential accelerant for structure formation. If the early universe contained seed magnetic fields, even at microgauss strengths, they would affect how gas cooled and collapsed into the first structures. Magnetic fields resist compression perpendicular to field lines while allowing collapse along field lines. This creates a tendency toward filamentary structures and can accelerate collapse in certain configurations. The origin of cosmic magnetic fields remains debated. They might have been generated during inflation through quantum fluctuations of the electromagnetic field stretched to macroscopic scales. They might have been produced during phase transitions in the early universe when symmetries were broken and the electromagnetic force separated from the weak force. They might have been generated by battery mechanisms during the formation of the first structures. Each scenario predicts different field strengths, correlation lengths, and spatial distributions. Observations of magnetic fields in galaxies, clusters, and intergalactic space show that fields with microgauss strengths exist throughout the cosmic web. These fields appear to pervade even under-dense regions like voids, suggesting that magnetism is a ubiquitous component of cosmic structure. But tracing their origin by observing fields in increasingly distant and younger systems has proven difficult, because field strengths in low-density environments are extremely weak. If primordial magnetic fields existed with sufficient strength, they would leave imprints on the cosmic microwave background through Faraday rotation of polarized light and through the alpha-Van wave perturbations they would generate. Current observations place upper limits on primordial field strengths at a few nanogauss on large scales. This is strong enough to be dynamically relevant during structure formation, but weak enough to avoid conflicting with cosmic microwave background observations. Even nanogauss fields could significantly affect early structure formation. During the cosmic dark ages, before the first stars formed, magnetic pressure could have modified the gene's mass, the minimum mass required for gravitational collapse. Lower gene's masses would allow smaller gas clouds to collapse, potentially creating more small-scale structure. Higher gene's masses would suppress small-scale collapse, forcing structure formation to proceed primarily through large-scale collapse. The effect depends on the field geometry and evolution. If fields were tangled on small scales, they would provide isotropic pressure that generally resists collapse and raises the gene's mass. If fields had coherent structure on large scales, they would create an isotropic collapse that produces filaments more efficiently than spherically symmetric collapse. The earliest simulations, including magnetic fields, show tantalizing hints that magnetism accelerates filament formation, but the parameter space remains largely unexplored. Cosmic strings, if they exist, would produce entirely different effects. These one-dimensional topological defects would have tensions approaching the grand unification scale, making them extraordinarily massive despite their thin cross-sections. A cosmic string passing through a region of space would gravitationally attract matter, creating wake structures of enhanced density that could seed galaxy and cluster formation far more efficiently than simple density fluctuations. The wakes behind cosmic strings would naturally produce filamentary structure aligned with the string trajectories. If strings formed a network that evolved over cosmic time through intersections and loop production, this network would create a cosmic web of wake structures. Galaxies and clusters forming in these wakes would naturally align in filaments and sheets, potentially explaining both the observed cosmic web morphology and the rapid structure formation timescales. Current observations place stringent constraints on cosmic string tension. The cosmic microwave background shows no clear evidence for the temperature discontinuities that string wakes would create. Gravitational wave observations limit the energy density in a cosmic string network, but exotic string models with smaller tensions or screening mechanisms might still be consistent with observations while producing observable effects on structure formation. Domain walls, two-dimensional topological defects, would create different signatures. These surfaces of concentrated energy density would evolve through the expansion, creating regions of enhanced and suppressed structure formation depending on their geometry and evolution. But long-lived domain walls are strongly constrained because they would come to dominate the universe's energy budget, violating multiple observations. If domain walls existed, they must have disappeared early in cosmic history, leaving only indirect imprints on structure formation. The accumulated evidence points toward a universe where structure formation proceeds through mechanisms beyond those currently included in standard simulations. Whether the explanation involves modified gravity, exotic dark matter, primordial magnetic fields, topological defects, or some combination of processes, the observational fact remains that structures exist that should not, according to our best models. This brings us to the most disturbing possibility of all, that the universe itself has changed its rules. The physical constants and forces we measure today might not have been identical in the early universe. If fundamental parameters evolved over cosmic time, the formation of structure would have proceeded according to different physics than what we observe locally, creating legacies of that different physics encoded in the earliest structures. Variable fundamental constants represent a radical departure from standard physics. The fine structure constant determines the strength of electromagnetic interactions. The gravitational constant sets the strength of gravity. The masses of elementary particles like electrons and quarks determine atomic structure and chemistry. In standard physics, these constants are assumed to be unchanging across all space and time. But some theories predict constant evolution. String theory with extra dimensions suggests that fundamental constants might depend on the size and shape of those extra dimensions. If the extra dimensions evolved during cosmic history, the constants would change accordingly. This could produce an early universe where gravity was stronger, electromagnetism was weaker, or particle masses were different, dramatically affecting how structure formed. Observations of distant quasars provide tests of constant evolution. Light from quasars passes through intervening gas clouds that imprint absorption lines on the quasar spectrum. The wavelengths of these lines depend on atomic transition energies, which in turn depend on fundamental constants like the fine structure constant. By measuring absorption line wavelengths from different cosmic epochs and comparing them to laboratory values, we can test whether constants have changed. Current observations suggest that if the fine structure constant has changed, it has done so by less than 1 part in a million over the past 10 billion years. This places tight constraints on many constant evolution theories. But it does not rule out more rapid evolution in the very early universe, before the epochs accessible to quasar absorption line studies. If constants changed significantly during the first billion years and then stabilized, current observations would not detect the evolution. Variable gravity during early structure formation could explain rapid assembly. If the gravitational constant was larger in the past, structures would have collapsed more quickly because gravitational attraction was stronger. This would compress the formation timescale, allowing massive galaxies and clusters to assemble faster than standard physics permits. As gravity weakened to its current value, structure formation would slow, naturally explaining why we see massive early structures but do not observe similarly rapid formation today. But changing the gravitational constant affects many observables beyond structure formation. It influences Big Bang nucleosynthesis, the production of light elements in the first few minutes. It modifies the expansion rate during recombination when the cosmic microwave background was released. It changes gravitational wave luminosities from binary systems. Any variation must simultaneously satisfy constraints from all these domains, severely limiting the allowed evolution scenarios. Phantom energy offers another route to accelerated structure growth. This hypothetical form of energy has an equation of state parameter less than -1, making it even more exotic than the cosmological constant. Phantom energy becomes denser as the universe expands, eventually overwhelming all other forms of energy and tearing apart bound structures in a big rip. But before that catastrophic end, phantom energy would modify structure formation in specific ways. During early epochs when phantom energy's density was lower, its effects would be small. Structure formation would proceed normally. But as phantom energy grew in density and importance, it would begin to dominate structure formation dynamics. In underdense regions, phantom energy would accelerate void expansion even more dramatically than a cosmological constant. In dense regions, it might suppress further collapse, freezing structure formation at a specific epoch. The observational signatures of phantom energy include faster void expansion than standard dark energy predicts, matching what we observe in the KBC void. It would also predict an accelerating increase in the cosmic expansion rate over time, a testable prediction through precision measurements of expansion at different redshifts. Current constraints suggest that if dark energy is phantom, its equation of state must be very close to -1, less than 5% deviation from the cosmological constant value. Emergent gravity represents perhaps the most radical alternative. In this framework, gravity is not a fundamental force, but an emergent phenomenon arising from the thermodynamic properties of spacetime itself. Just as temperature emerges from molecular motion without being a fundamental quantity, gravity might emerge from underlying microscopic degrees of freedom associated with spacetime structure. If this picture is correct, gravitational dynamics might deviate from general relativity in regimes where the emergent description breaks down. The entropy of spacetime would play a crucial role in emergent gravity. Black holes have entropy proportional to their horizon area, suggesting that spacetime itself carries information in a holographic manner. If the universe's structure formation involves significant changes in spacetime entropy through the creation and growth of black holes and cosmic horizons, this could modify gravitational dynamics in ways that standard general relativity does not capture. Testing emergent gravity requires identifying observables that distinguish it from general relativity. One prediction is that gravity should modify in situations involving large horizon areas, such as the universe's cosmological horizon or the boundaries of large voids. If true, this would naturally explain enhanced void expansion as an emergent gravity effect occurring near the void boundaries, where horizon-like structures might exist in the spacetime geometry. But emergent gravity faces severe theoretical challenges. Deriving general relativity from more fundamental thermodynamic principles requires assumptions about the entropy-area relationship and the temperature associated with causal horizons. These assumptions are difficult to justify from first principles and lead to predictions that conflict with some observations. Current formulations of emergent gravity struggle to reproduce general relativity's successes while producing distinctive new predictions that explain anomalies like rapid structure formation. The possibility that we fundamentally misunderstand gravity itself cannot be dismissed. General relativity has been tested extensively in the solar system, in binary pulsars, and through gravitational wave observations. It passes all these tests with remarkable precision, but these tests occur in specific regimes: strong gravity around compact objects, intermediate gravity in binary systems, and dynamical gravity during mergers. We have never directly tested gravity in the regime relevant to void dynamics. Weak gravity over enormous distances in extremely low-density environments. This is the regime where modifications are most likely to appear. Theories can be constructed to match general relativity exactly where it has been tested while deviating in untested domains. Screening mechanisms specifically arrange this behavior, preserving general relativity's successes while opening the door to modifications where observations are lacking. If nature employs such mechanisms, our confidence in applying general relativity to cosmic voids might be misplaced. The ultimate test requires observations in the untested regime. This means measuring void dynamics, gravitational lensing by voids, void galaxy velocities, and other observables that probe gravity in low-density environments. The technical challenges are enormous because voids contain few galaxies, and those that exist are faint and difficult to characterize. But upcoming surveys will dramatically improve the data quality, providing tests of gravitational physics in regimes never before accessible. Whatever the explanation for structures growing faster than expansion, the phenomenon forces us to acknowledge limits in our understanding. Either our models are incomplete, our measurements are biased, our theories are wrong, or the universe has properties we have not yet discovered. None of these options is comfortable. Each requires revising fundamental assumptions and accepting that our cosmic picture remains far from complete. The pace of discovery accelerates. Every new observation from JWST reveals structures that challenge expectations. Every refinement in Hubble constant measurements deepens the tension between local and global values. Every survey of cosmic voids finds larger and deeper underdensities that strain theoretical predictions. The universe is not cooperating with our models. It is producing phenomena faster, larger, and stranger than our theories anticipate. And we are forced to watch, measure, and question. The structures growing faster than space itself are not abstract curiosities. They are the architecture of the cosmos, the skeleton upon which galaxies hang, the framework determining where stars form and where life might emerge. If we do not understand how these structures form, we do not understand the universe's basic organizational principles. We are mapping the surface while missing the mechanism beneath. The expansion of space should be absolute. It should set the ultimate speed limit for cosmic structure growth. Nothing should outpace it except objects moving through space at relativistic velocities, and those objects cannot build gravitationally bound structures. Yet we observe structure assembly, void expansion, and black hole growth proceeding at rates that exceed what expansion dilution should permit. The universe is building faster than it should be able to build. This might be the most profound discovery of the JWST era. Not any single object or structure, but the accumulated pattern of anomalies that all point in the same direction. Cosmic evolution proceeds faster and more efficiently than our models predict. Whether through super-Eddington accretion, direct collapse formation, enhanced void expansion, modified gravity, or mechanisms we have not yet imagined, the universe is assembling its architecture on accelerated timescales, and we are left with questions that cut to the foundation of cosmology. Is the Hubble constant truly constant? Is dark energy truly uniform? Is general relativity truly complete? Are our measurements truly representative? Is our location truly typical? Each question challenges core assumptions. Each has profound implications for what we think we know about the cosmos. The answers will come through observation, more distant galaxies, deeper surveys, precision measurements of velocities, lensing, and clustering, detailed maps of voids and their dynamics, spectroscopic characterization of early black holes and massive galaxies. Every observation constrains possibilities, narrowing the space of viable theories until only those that match reality survive. But the process is slow. Cosmic timescales dwarf human lifetimes. The structures we study evolved over billions of years. The observations required to understand them span decades. We are snapshots attempting to understand a film, single frames trying to grasp the narrative arc. Our progress is real but incremental, each discovery adding one more piece to a puzzle whose final picture remains obscured. What we can say with certainty is that something is growing faster than space itself. Multiple somethings. Voids expanding beyond predictions. Black holes accreting beyond limits. Galaxies, assembling beyond timescales. Filaments, extending beyond models. Each represents a process that outpaces the cosmic expansion, building structure through mechanisms we do not fully understand. These are not measurement errors. The data is too consistent across multiple independent observations. They are not statistical flukes. The phenomena are too common and too systematic. They are not misinterpretations. The theoretical predictions are too clear, and the discrepancies too large. These are genuine anomalies pointing toward physics beyond our current grasp. The universe is speaking. It is telling us, through its structures and their impossible growth rates, that our models miss something fundamental. Whether that something is a new force, a modification to gravity, an unexpected property of dark matter or dark energy, or something we have never conceived. It operates throughout the cosmos, shaping evolution in ways we are only beginning to recognize. We stand at the boundary between the known and unknown. Our instruments reach far enough to detect the anomalies. Our theories are developed enough to make precise predictions that observations can test. The gap between prediction and observation has never been clearer. What we do with this knowledge determines whether we progress toward truth or remain trapped in comfortable but incomplete models that fail to capture cosmic reality. The structures growing faster than space are calling us toward new physics. They demand explanation. They resist incorporation into standard frameworks. They persist across every new observation, refusing to disappear or reconcile with expectations. They are the universe's way of forcing our hand, compelling us to either revise our theories or admit that we occupy such an unusual location that our observations cannot be trusted. Neither option is satisfying. Both represent failures of our cosmological program. But one is truth and the other is denial. The choice is whether we accept what the universe shows us or cling to models that no longer match observation. Science demands the former even when it is uncomfortable, even when it overturns decades of work, even when it forces us to admit that we understood less than we thought. The universe does not care about our pride. It does not adjust itself to match our equations. It simply is operating according to principles we must discover through observation and reason. And right now, it is teaching us that structure can grow faster than the expansion that should limit it, through processes we have yet to identify but cannot ignore. If this revelation unsettles you, if the cascade of impossible structures and violated limits has made you question the cosmic foundations, then you have grasped what is truly at stake. This is not esoteric academic debate. This is the fundamental architecture of reality refusing to conform to our models. Like this video if you want to see science confront its limits. Subscribe to this channel if you understand that the universe's greatest discoveries come not when observations confirm our theories, but when they shatter them completely. Because what comes next will test every assumption we have made about how the cosmos operates and whether we can trust anything we think we know about space, time, and the growth of structure itself.